A very warm and good morning to all of you. Now we are going to start our new topic, that is singularity. How will we define singularity? A point at which a function of z is non-analytic is called a singular point, and this property is called singularity because of that point. So singularity is directed with analyticity of the function about that point. Suppose we have a function, you can clearly see z equal to 2, it becomes infinite. So function is not defined at that point. So eventually it will not be analytic at that point. So z equal to 2 will be a singular point. Now there are certain types of singularities. First is isolated singular point. Suppose we have a function and it is varying like this. So we have a singular point like z equal to 2 and 3. Now for certain a plus, we take a very small element epsilon, and if we are taking limit epsilon tends to 0, there should not be any point about that singular point. Means that point should be isolated in a certain region, in a very small region epsilon. If z equal to a is a singular point of function of z and there is no other singular points within a small circle of radius epsilon tends to 0 surrounding that point, then z equal to a is called a isolated singular point. Very simple, as I explained you. Suppose it's z equal to 2 and we are drawing a circle z equal to 2 and a small element epsilon is there. So there should not be lies any other singular point in this region. Then it will be called a isolated singular point. Now we'll study about Taylor series. We have studied it earlier in our previous classes, but now here we are again going to study Taylor series. What is Taylor series? Function of z is there and it is a analytic function inside a circle C, and circle has a center at z equal to a. So for z inside that circle, inside that region, function of z will be function of a plus first derivative function of a z minus a f double dash a by factorial 2 z minus a square, and it will continue to n f n a factorial n z minus a to the power n. Now if the circle has center z equal to 0, so at z equal to 0, what will expansion the function of z? It will be f0 plus f dash 0 z f double dash 0 factorial 2 z square, and similarity will goes on. Now there are certain questions we will do. Suppose we have function f of z equal to sin z, then Taylor's expansion will be function of a plus function of a derivative function of a z minus a plus f double dash a by factorial 2 z minus a square plus f triple dash a by factorial 3 z minus a cube, like this goes on. So function of z will be, a point is z equal to 0, so sin 0 is 0, then sin z, derivative of sin z will be cos z, and cos 0 is 1, and a is 0, so z will be only there. Now cos z integration, cos z differential will be minus sin z, and sin z 0 it will be sin 0, so it will again 0, and then 1 upon factorial 3, and sin z will be cos z, z minus a cube, so cos 0 will be 1, and a is 0, so z cube will be there. So about z equal to 0, we have expansion of the function of f z equal to sin z is z minus z cube by factorial 3, z5 by factorial 5 minus z7 by factorial 7. Similarly for cos z, function of z about z equal to 0 is 1 minus z square factorial 2, है ना. Cos x, you know the value of cos x, 1 minus x square upon factorial 2 plus x cube upon factorial 3. In sine function odd terms will be there. In cos function only even terms will be there. Remember that. In sine functions, expansion of Taylor series expansion of sine function, z minus z cube by factorial 3 plus z5 factorial 5 and so on. But in the expansion of cos z, 1 minus z square factorial 2 plus z4 upon factorial 4 minus z6 upon factorial 6. Similarly, for e raised to power z, we'll get 1 plus x square upon factorial 2 plus s cube upon factorial 3 plus x upon factorial 4. Now, suppose we have a function 1 minus z raised to power m. So we know there is an expansion of function of z at z equal to a. What is f of a plus f dash a z minus a plus f double dash a by factorial 2 z minus a square and so on. So put z equal to 0, so we'll get 1. Then differentiation, so m will be coming out and x raised to power n equal to x raised to n minus 1. So this will be there, z equal to 0 only, m and z minus a, so z equal to 0 only, z will be there. And similarly for like this double derivative function will be mm plus 1 by factorial 2 and a equal to 0, so it will be z square remaining. Similarly mm plus 1 m plus 2 will be there, factorial 3 will be there, and z minus a cube a 0, so z cube will be there. Again we have a new function log 1 plus z. So function of z will be function of a prime z minus a f double dash upon factorial 2 z minus a square. Put a equal to 0, so log 1 will be 0, log 1 plus z equal to 1 upon 1 plus z into z, so z will be there, and 1 upon 1 plus z equal to 0, so 1 will be there, coefficient, and log 1 plus z double dash, so minus 1 upon 1 plus z का whole square, so dash will be there, and factorial 2 will be there, and 1 will be in coefficient, it will go on. You can solve it with the help of this function also. We just have calculated the value of this function. Simply put integration of 1 plus z dz. So 1 plus z dz can be expressed as 1 minus z raised to power m equal to 1. Now put m equal to 1 this formula and you will get answer like this, and just integrate z minus z square upon 2 plus z cube upon factorial 3 minus z4 upon factorial 4, sorry z4 upon not factorial 4 only 4, and it will goes on to infinity. Now we have a function, so just factor it. You will have 2 points, z equal to 1 and z equal to 2. We using partial fraction method. Function of z will be, so you can break it in a upon z minus 1 plus b upon z minus 2, and by solving this equation you will get a equal to minus 1 and b equal to plus 1. So put a equal to minus 1 and b equal to plus 1. Now you have two different functions here. First function is 1 upon 1 minus z, and second function is minus 2 will be outside, so 1 minus z by 2 will be there. Okay, so again use this expansion 1 upon 1 minus z to the power m, so 1 minus z to the power m equal to 1 for this, so it will be 1 plus m equal to 1, so 1 plus 1 z will be there for m equal to 1. And for this put z equal to z by 2 here and m equal to 1, so what will you get? You will get 1 by 2 plus 3z5 plus 7z square by 8 and so on. So with the help of this formula you can solve this. If you don't want to use this formula, then you can also solve this. Simply use Taylor series expansion, that is function of a So z equal to 0, function of a 1 will be there, and z minus a f dash a, use this, and similarly for this, and you will get same answer is written here. Now, if function of dash is an analytic function in the ring shaped region R bounded by two concentric circles equal C2 of radii R and R1 with center z equal to k, and for all z in R. So what is low-end series expansion? Function must be analytic. Here in all terms, all series expansion, we have to use only analyticity of the function, and function must be in ring shaped region R, and function center should be z equal to a. So now we can expand low-end series expansion. And now this certain condition must be satisfied. Center must be z equal to a. It should be a ring shaped, and function must be analytic. So function of z will be a naught plus a1 z minus a plus a2 z minus a square plus dot 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 to infinity plus b1 1 upon z minus a plus b2 1 upon z minus a square, and so on, where n is 1 by 2 pi iota fw by w minus a n plus 1 dw, and bn is 1 upon 2 pi iota fw w minus a n minus 1 dw. Suppose we have integration in closed contour C prime, where C prime is C minus C1, similarly defined here like this, and we have to integrate this. So we are using integration by parts, n and bn, fw by w minus z dw for C, and fw by w minus z wy, because we have no formula to calculate directly for this reason. So what will you do? We will calculate whole C and whole C1 integration in this region, and then we will minus subtract from this to this, then we are left with this only region. Now singularities. Suppose f of z is a function having singularity z equal to a, an analytic function at all other points, then its low-end series expression will be, at z equal to a, it is analytic. About z, similarly a naught a1 plus z minus a2 z minus square, bm z minus a to the power m, b2 z minus a square, and b1 z minus a only will be there. Now types of singularities. First, removal singularity. We have studied isolated singularity in our first equation of this lecture. Now if all the coefficients of b1 b2 and all b's are 0, okay, when will removal singularity arise? When this all b's are 0, then function of z will be a removal singularity at z equal to a. Example, function of sin z upon z. When you expand it, you will get only a not a1 terms, but you are not getting b1 terms. So b1s are 0, then you have only singularity sin z by z. How it is happening? At z equal to 0 is a singular point, we can clearly see, because z equal to 0, it's a function is not analytic at z equal to 0. Sorry. So it's a isolated singular point. Now expand sin z, and there it is z minus z cube upon factorial 3 plus z5 upon factorial 5 minus z7 upon factorial 7, and so on. So when you expand sin z by z, it will goes like this: 1 minus, just divide this by z, you will have this. You can clearly see there is no denominator term where z raised to the power m, because z is 0 here, a is 0, so in denominator z raised to the power some term, and there is no denominator z here, so all these are 0 here. So function of z has isolated and removable singularity point z equal to 0. Now again, you can take the function sin z by z square. So sin z is this, just divided it by z square. So you are having this. Now you have a b, that is 1. Okay, so fz has isolated and non-removable singular point at z equal to 0. Okay, in multiple choice questions he will give statement. For statement you have to choose one: isolated, removable, isolated, non-removable, poles of order 1, and like this. So you have clear cut knowledge about these things. Now we study about poles. Only finite number of b's are non-zero, then fz has a pole at z equal to a. If fz has a pole, then we will expand Lorentz expansion of function. We'll have this expansion, and now we will have b's, means b's are not equal to 0. Now in this case, function of z has a pole of order m. Okay, if pm not equal to 0, then same order of the will take place by the pole. Here b1 was not 0, so z equal to 0 has a pole of order 1. Look in the function, z square will be there, but it is not have pole of order 2, it is pole of order 1. Why? Because we are expanding it and dividing it, we are getting b equal to 1. That's why Lorentz series are very important here. First expand according to Lorentz series and then check coefficient of z minus x to the power m. Okay, if it is non-zero, then only it will have removable singular point and pole of order that point. Now similarly we just have done here. Now essential singular point. If infinite beams are non-zero, then f of z is an essential singular point z equal to a. है ना? You know, if many m's till infinity dot 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 are non-zero, means 1 by z at coming to infinity, then only we will say it is a essential singular point. Now how we will determine steps to find out singularity? First, limit z tends to a f of z exists and it is finite, means limit of that function should be exist. Then z equal to is a removable singular point. First we will check removable singular point. We have just studied when we will have removable singular point, this all b's are 0, then we will have removable singular point. And in order to define removable singular point, you have limit z tends to a sin z by z. Now in next process we will do limit z tends to z. If limit is not existing, then at z equal to a, then z equal to is an essential singular point. If limit is not existing, है ना, these steps are also true, but we can check singularity with this point in order to solve numerical very quickly. First we will check limit. If limit is defined, then function is removable. If limit is not defined, then function is essential. Function has essential singular point. And if limit z tends to a z minus a m f of z existing, it doesn't exist, but if we are putting coefficient z to power minus a m exist, then it is finite. Then function of z is pole of order mz equal to a. Now take example. This was the function, and limit z tends to 0, z1 f of z exist, and it is giving limit 1. So it is has a singularity of point pole of order 1. Like this we will calculate singularities. Thank you. We will study next in our further classes. Thank you very much.